Hi everyone. Today's cost-centric mindset for DRAM fabrication makes the DRAM latency not scale as much as its cell density. Before going to the details, let's talk about some DRAM basics. This is a structure of DRAM chip. Each chip has multiple banks, and each banks have multiple subarrays, and all subarrays share global sense amplifier. The subarray consists of multiple tiles. Each tile has 512 word lines and 512 bit lines. The bit lines are connected to the local sense amplifier. The intersection of the local word line and bit lines is a DRAM cell, which has a transistor and a cell capacitor that store logic bits 0 and 1. DRAM operation has multiple commands. Basic reading and writing involve charging and discharging of the local and global bit line. And the capacitance of both bit lines depends on their length. This capacitance value is the major contributor to different timing parameters as shown in this table. This timing parameter dictates the DRAM access latency. Therefore, reducing DRAM latency requires reducing the local and global bit line lengths. So one way to reduce the latency is to reduce the length of local bit line. The figure here shows a DRAM bank that contains 512 cells per bit line in each subarray. Zoom in the tile, you can see the bit lines connect to the local sense amplifier, the precharge unit, write driver, and the sense amplifier I/O. The total length of this circuit block is about 1/4 of the bit line. This figure is showing 256 cells per bit line structure with the same bank capacity. The required number of subarray had doubled, therefore the length of the global bit line, which goes across the bank, has increased. From our latency area trade-off analysis, we can see that the overall access latency increases while we are shortening the local bit line. Therefore, there's a need to simultaneously reduce both local and global bit line length in a way that does not substantially increase the DRAM bank area. So Monolithic 3D technology enables processing and integration of multiple tiers of logic circuits on the same die. Compared to the traditional 3D structure that uses through-silicon vias to connect different dies together, monolithic inter-tier vias of M3D technology has 10,000 times smaller dimension than the TSV, so that we can achieve very fine-grained vertical interconnects on the single die. For designing DRAM with M3D technology, our idea is to put the sense amplifier on one tier and the DRAM cell array on the other to improve the latency area trade-off. But the challenge are due to the limitations of M3D fabrication process. We need tungstens to realize the interconnects at the bottom tier, which has worse resistivity than the traditional copper interconnect. At the top tier, the transistor performance degrades due to the required low temperature M3D fabrication process. To overcome these challenges, our proposed idea for designing M3D DRAM is to place the DRAM cell array on the top tier to avoid the interconnect performance penalty. We put the sense amplifier and the other peripherals on the bottom tier to avoid transistor degradation. As you can see in figure C, in our proposed M3D DRAM design, we can reduce the local bit line length to 128 cells per bit line and still achieve the global bit line length shorter than the conventional 2D DDR4 design. Let's look at the cross-section of the vertical interconnect. The local word line driver connects to the local word line through metal 1 to metal 5 and MIVs. The same method applies to the sense amplifier connects to the local bit line, and sense amplifier I/O connects to a local data line. Our analysis shows the extra resistance and capacitance from the vertical interconnects actually does not increase the latency or energy consumption significantly. We analyzed the timing constraints and an area with LT spice and cacti. Our analysis shows that the M3D can relax the latency area trade-off by moving the trade-off curve closer to the origin. We select DDR4 with 512 cells per bit line and M3D DRAM with 512 and 128 cells per bit line for our system level analysis. We do a Gen 5 and NVMe based full system simulation with PARSEC benchmark application, and the result shows 9.5 less latency and up to 21% less energy delay products with 14% less DRAM die area compared to a conventional DDR4. In conclusion, we show how the fundamental latency area trade-off for DRAM can be mitigated by using M3D technology. We evaluate the latency area trade-off for various configurations. Our design is quite beneficial. Thank you.